Okay, so the last thing we have here for recursion is Towers of Hanoi, but I'm gonna skip this for now. It's not overly important. It's a rather, I don't want to say it's complex. There's a really, you know this game, right? The trick is move everything from one of the pillars to the other, but you're only allowed to move one disk at a time, and every disk that's moved, every other disk that's not being moved must be on one of the pillars, and it can't be placed below a disk that's bigger than it, right? That's the game. And here's the recursive algorithm for it. Here's how you move all the disks. It's simple. You move all of the disks but the bottom one to the middle peg. Then you move the bottom peg to the destination peg. And then you move the n-1 disks from the middle peg to the destination peg. Easy, right? And you're like, well, hold on. I was saying it in a way where you're left going like, well, it feels like you skipped a step. You're allowed to move one at a time, and you just said move them all. How do you move them all? Oh, well, you move the n-1 minus 1 ones to, and so on and so on. But I'm not going to go into it right now for the sake of time. All right, searching. We've talked about searching before. In fact, we covered the two core searching algorithms I really care about. We've talked about linear search. We've been talking about linear search since like the first month of 161, in variations of it at least. If you didn't realize, assignment 1 of 161 was basically a linear search. Except you weren't looking for a single thing, you were looking for how many of each thing fell within that latitude-longitude square, remember? For each thing, it's still like a linear, you're going through this linear collection one at a time. But we also talked about another search, that binary search thing. Raise your hand if you remember what that is, right? And I remember I played that game of pick a number between, here, give me a second here. If you don't remember, let's just do it again really quick here. So, I need a volunteer. Someone just raise your hand. Let's give someone you, okay? You're going to pick a number between 0 and 1023, but don't tell me. Okay, have it in your head. Any number, okay? Tell the two people behind you so they can confirm that that everything's good. I won't look, I promise. Okay, you're good. Now, if I were to do a linear search, how many things would I have to look at to guarantee that I find the number that you picked? 1024, right? Because 0 to 1023. So I'd have to look at all of them to guarantee that I found it. But I can guarantee I'm going to find your number in no more than 10 guesses, right? So it'll either be 10 guesses or less. I'll get your number. But I'm going to ask you higher or lower. And you're going to say higher or lower to guide me. That's it. That's the only thing. But by doing so, instead of taking 1,024 different guesses, I can do it in 10. So my first guess, is it 512? Higher. Is it 768? 640? 704? 672? 656? Lower, okay. 648? 652? 650? 650. And how many guesses was that? That was 1, 2, 3, 4, 5, 6, 7, 8, 9. I got it in 9. So why did that work? Well, first of all, it worked because the data was sorted. Now, obviously, it's not really sorted, it's just a single number. But I was able to traverse the numbers in a way as if like the order mattered, right? There was an orderedness to those numbers. I was able to go higher or lower, and that directionality helped me narrow in where I found it. So what I did is I picked the number right in the middle, 512. Then he said higher. So I picked the number between 512 and 1023, which was 768 or something, I can't remember, right? So I always went in the middle. Every time I made a guess, I would go halfway towards the other like endpoint. So that's how I did it. And because of that, I was able to figure it out in way less guesses. So what's better, 1,024 guesses or 10? Obviously 10. And what's interesting about this is if I double the input size, if I double the number of numbers, meaning I have 2,048 numbers, and I was doing a linear search, it would take 2,048 guesses to guarantee that I found it. I would double the number of guesses I would need. But with this binary search idea, doubling the input size only makes me take one more guess. I would only need 11 in the worst case scenario, which is a lot better. So, searching. For the context of what we're going to do right now, we are going to say, okay, we're looking for some specific thing in some collection to know if it exists within the collection or not. That's what we're going to say we're searching, right? You should be familiar with this problem. Does a given number exist within an array of numbers, for example? And to write an algorithm to solve this problem, all we need is something that says if it's there or not. That's all that's required. Any algorithm that will do that and is correct is sufficient. But the focus here will be on two intuitive ideas that people commonly lose. Linear search and interpolation search. That's the binary search, right? Binary search is a specific version of interpolation search. Yeah. Throughout this topic, the things being searched will be referred to as a needle, and the thing being searched through will be the haystack. So we're looking for a needle in a haystack. So linear search. Here's the algorithm. And I want to be clear about what the algorithm is. The algorithm is not the code. It has nothing to do with Java or Python. The algorithm is like, what's the process? What's the idea? And here's the idea. Start at the beginning of the haystack and sequentially look at each element until the needle is found. If we ever see the needle, it's there. We can conclude that the needle is in fact there if we find it there. If we get to the end of haystack and never found what we were looking for, that's when we can finally conclude that the thing is in fact not there. I know I hit this point really hard frequently over the last year. I know that the thing is there the moment I find it. I only know it's not there after I've exhausted all possibilities. Cool? So yeah, this algorithm, there's no more details than that because we really don't need any more details than that. How you go and implement this, it's up to you as long as you're following that algorithm. Yeah, high level, abstract. Okay, the computational complexity of this is linear. Big O-N. Worst case scenario, every element is looked at before we can make a conclusion. It's linear. Best case scenario is, well, it's the first element. Great, we found it in one guess. Lucky. But, you know, on average, it's going to be somewhere in the middle, right? For every time the number might be the first element, it might be the last element, right? You know, given random chance. So on average, it's going to be about somewhere in the middle. So that's like n over 2 we'd have to look at. But of course, a half times n over 2, same thing. That's just like a coefficient. We don't care about coefficient. It's linear. Cool? Cool. So yeah. All right. Cool. There we go. There's a linear collection. When With a linear search, to guarantee if some needle exists within the haystack, each element must be looked at. Right? I can only conclude that 16 is not there after I look at all of those things, find that 16 is not there, and go, well, 16 is in fact not there. Any questions? This should be review, but if there's a question, now's the perfect time to ask before I carry on. So here is an iterative linear search. Mind the fact that it's got like the T there in the definition. I've got it as a static method. Yeah, that's all, just FYI. This method here, it's not going to return true or false. It's actually going to return the index of the element, just a slight variation. So return the index of the element if it exists within the haystack. And if it doesn't exist, return some special not found value. Okay? So I'm looking for, it's generic type T, so I'm looking for some needle of type T in an array of type T. This could have been a list, this could have been a stack, whatever, just some linear collection. I'm using an array for simplicity. And what do? For I from 0 to the length of the haystack, check each thing. If I find it, return the index, and if I ever finish that loop, having never returned the index, it's clearly not there, return not found, which is just some sentinel value assigned to some constant there. Questions? You've seen this algorithm in its variations, I don't even know how many times at this point. A lot, right? You've seen variations of this algorithm so many times, both in Java and in Python, right? Questions? Anything? Yeah, so start at 0. If the element's at index I, then conclude that it's there, return I. Increment I otherwise, keep going till you get to the end. Am I beating a dead horse at this point? Okay, good, good. So here's a recursive implementation. It's the same algorithm, it's just written recursively, so there's no loop. But take a moment and look at this code and make sure it makes sense. I've got this function, recursive linear search. Notice that it has 3 parameters. The thing I'm looking for, the haystack, and the current index. So I check, is the current index equal to the length of that array? If it is, we're looking at the end of the array. Therefore, it's not there, right? Right? If I'm ever at the end of the array, then it's not there. Cool? If you're not convinced yet, let's work through the other 2 parts, and then maybe we kind of come back to this base case here. Because that's one of the 2 base cases. This recursive function has 2 base cases. If we're at the end of the list, or the array, then we didn't find it. If the haystack at current index is what I'm looking for, well then return the index, return current index. I found it. That's the other base case. Otherwise, if we're not at the end and we haven't found it yet, call recursive linear search for the needle in the haystack, those don't change, at current index plus 1. When I call this function for the first time to perform a linear search, what do I call? What arguments do I give it? Needle, haystack, and 0. I want the linear search to start at index 0. I think I have that as like the next chunk of code here. Yeah. If I wanted to call this method, I would start it with current index at 0. Recursive linear search, some needle, some haystack, 0. So let's talk through this. Some needle, some haystack, and it starts at 0. Let's say the array is some arbitrary size. Let's say it's 5, whatever. So is 0 equal to the length of the haystack? Is 0 equal to 5? No. All right. Is the thing, now I'm looking at the second, the else if, is haystack at 0 needle? If it is, return true. Otherwise, call the recursive method again with needle haystack, but this time it'll be 0 plus 1 will be the current index. So 1. So go to the beginning of the function. Now current index is 1. Is 1 equal to 5? No. Is the haystack at index 1 the thing I'm looking for? If it is, return the index. If not, call the recursive one again, except this time current index will be 2. And then 3. And then 4. And then eventually it'll become 5. 5 is equal to the length. We hit the other base case. Not found. Any questions about this one? Yes?
Is there a way to set that up where you wouldn't have to put in the current index as an argument?
What?
Since it's called itself, if you had it as like as a variable,
Yeah.
you reset it to 0 every time. But is there a way to set it up?
So you're going to want to, so I think I know what you're getting at. I think maybe, and I think you actually asked that question in lab yesterday. We're going to need the current index to be some value we can give the function. It needs to know what index it's currently looking at. And one thing you'll notice is a lot of times with these recursive methods, the recursive methods, functions tend to have no states in them. What's up?
Which if we run first? Because I'm saying, what if the last element in the index is the needle?
Well, remember that the last valid index is index 4, right? But the length of the haystack would be 5, right? Yeah, cool. But back to your question, often what you do is, for example, imagine that I didn't say, like right here at the bottom, I said, well, if I want to search something, I would call this, right? Do I have an example of that? I do not. But if some like asshole came along and called this function but started the index at 5 for some arbitrary length array, it would start doing a linear search, but it would start it at index 5, not 0, which is kind of annoying, right? I mean, whatever, to each their own. Maybe there's a reason for that. But often what we do is we'll have like a setup function that would be called like linear search. You give it the needle haystack, and then that function just immediately calls the recursive one, but it starts at 0 always. So there's a bit of a workaround, and we're going to see examples of that as we carry on. Once we get to the binary tree stuff, we'll see some examples of that. But yeah, we need that argument. The parameters and argument is how we are communicating like what's like what the index is, the way I've written it. One thing I want to really stress here, I don't know if I can get them both in the same shot. This algorithm and this algorithm, it's the same algorithm. The code is different. One's recursive and one's iterative. But the algorithm is the same. Start at the beginning. Is this the thing I'm looking for? Yes or no. Go to the next thing. Is this the thing I'm looking for? Yes or no. Go to the next thing. It's the same algorithm. The code's different, quite different, but the actual underlying algorithm is the same. And that's interesting. But it hits a key point here. The algorithm is like the idea. Other questions about this?
Would you ever want to like throw an exception like initially if they were to put it as the last element, or does that kind of just take care of it?
That would kind of be hard to do here because you would never, no call would know should this have been the first call. Like it wouldn't have really known. That would be, I don't know how you would make that work. That shouldn't become an issue. But you typically, like imagine this existed inside some class. A lot of times, what I was just saying, how you have like this setup function that just calls this one with the proper initial starting conditions. Usually you would make this one private. And the one that does the setup is the public one. But we will see some pretty good concrete examples of this soon. Not today, probably not Tuesday, but soonish. Yeah. Other questions? I'll give you a second, think about it. I want you to make sure you're comfortable with this before I carry on. Yeah?
Sort of related to the first question I asked, but so you can't use a counter variable in a recursive method.
I could, but I have no way to communicate. If I make a counter variable, like current index isn't an argument, but I set like current index starts at 0 at the top, and then I increment it. That value, that current index variable, only exists within the current instance of the recursive linear search one. The next time it calls itself, it'll create another current index, but it starts it at 0. They are entirely independent from one another. So we're kind of stuck. There could be a way around it if you had side effects, where you had this update some like global variable or something. You could do that, but don't do that. That's bad. We don't like that. Please avoid side effects like that. That kind of spoils like the beauty of recursion once you start doing that. Now that said, there are some cases where maybe you do need to do something like that. To clarify what their question was, why not just create some current index as like a local variable inside this method? Don't have it as an argument. And then when you're done, increment it. And the reason that won't work is because as soon as the recursive call is called, we go and we start running recursive linear search again. But that variable that we would use as a counter variable will exist in both of those call frames for each of those instances, like for each time we call that method. And every single one is entirely independent from one another. They do not communicate at all. The only way to communicate these values between function calls is through arguments, like the parameters. It was a very good question. Thank you. So this is just showing you the interpolation search, the binary search, like the example I just did a moment ago. But this is saying like you do this all the time. If I tell you to open up page 554 in a 1,000-page textbook, you don't flip to the first page and go, is this page 554? No, go to the next page. Is this the one I'm looking? No, you don't do that. That's stupid, right? You go like, it's about probably in the middle somewhere. And if I do that and I turn to page 402 and I'm looking for page 553, I'm looking for page, I have a typo there. That's okay. Typo being, a moment ago I was looking for page 554, but now I'm saying I'm looking for page 553. But whatever. If I turn to page 402, and I'm looking for 500, does anyone have a textbook with them? Are you for real? Sure. Do I have any book or anything? You have a book? Well, don't worry about it. I open a book, right? And I'm looking at page 5. Yeah, toss it. No. I'll come around. I will use the book. If I'm looking for page, so how many pages we got here? 300-ish, right? And I'm looking for page 200. I open the book. I'm currently looking at page, I turned to page 200, so let's not do that. I'm looking at page 167, right? I've got the book like this. And if I'm looking for page 200, Like, look at the book for a moment, right? There's a bunch of pages over here, and there's a bunch of pages over here. And I'm looking for page 200. I'm currently looking at page 166 and 167. Which side of the book must the page 200 be on? It must be over here somewhere, right? Following that logic, it must not be over here. This is page 166 and 167. How many pages did I just eliminate from my search entirely? 166, all of these. So that's pretty good, and that's actually the magic of how this search is so good. Is every time we make a decision on which way to look, we eliminate big chunks of the search. So if I'm looking for page 200, let's say this is okay. I'm looking at page 254 now, right? And I'm looking for 200. Well, 200 must be in this area. Not over here. Not over here. We already concluded that. So it must be in here. So every time I make a decision here, can you hand this back to him? With a linear search, every time I look at a page and I conclude that that's not the thing I'm looking for, I eliminate one thing from my search. With that idea, with the binary search idea, or interpolation search, every time I make a decision, I eliminate, hopefully, in the binary search, which is the best case scenario, every time I make a decision, I eliminate half of the remaining things from the search. So that's why it's so much better, is there's so much more information I can gain from one check versus the linear search. Linear search, I eliminate one piece of information. Binary search, I eliminate half of the remaining information every time. So that's why it's so much better. Now, if we're thinking computational complexity, if I eliminate half of this stuff, and then another half, and another half, and another half, I'm dividing by 2 over and over and over again, right? And from what we remember, what do you think the computational complexity of a binary search is? Log base 2 of the size of the input. Why log base 2? Well, because I'm dividing by 2 every time. That's why. But there's the big catch with a binary search. The data must be sorted. If the data wasn't sorted, imagine all those page numbers weren't in order, right? Imagine how crazy that would be. And I turn to a page and I say, oh, I'm looking for page 200, but I'm looking at page 74. Which side is the page 200 on? Well, I don't know. I have no idea. There's no way for me to know because they're not ordered in any way in that weird example. So we can think of, for example, doing a binary search on the numbers 1 through 15. I could have done this example with the numbers 0 through 1023. Just tree would have been a little bit bigger. There would have been 10 levels in the tree instead of 1, 2, 3, 4. My first guess, if I wanted to pick a number between 1 and 15, my first guess would be 8. And if I'm right, good. If not, you say higher or lower. If you say lower, I guess 4. If you say higher, I guess 6. If you say lower, I guess 5. That's how we can visualize this, the guesses. In this particular example, what is the most number of guesses I would ever have to make? 4. 1, and why? Well, the furthest I could travel down that, we call these things trees. The furthest I could travel down this tree is all the way from the top to the bottom, and there's 1, 2, 3, there's 4. There's 4 levels to it. So that's as far as I'd ever have to go, which is great. Yeah, cool. Okay, see if there's anything in here that I didn't just say already. The reason it takes fewer steps, yeah, roughly half. Okay. Yeah, so for example, 15 is greater than 8. If I'm looking for 15 and I guess 8, I've eliminated 1 through 7. And the 8 also, because I guessed 8. So I eliminated like half of the stuff. The relationship, now this isn't interesting to note because this is going to be important going forward because we're about to shift to trees. The relationship between the maximum number of checks and the number of elements n in the haystack is that. N is going to be equal to 2 to the power of the height plus 1 minus 1. That's the relationship, right? Where h is the height of the tree, or the number of steps needed from the top to the bottom, or we can rearrange it a little bit to be, well, the height is equal to log base 2 of n plus 1 minus 1. To be specific, but yeah. So the height is related to the log base 2 of n. We could n plus 1 minus 1, but that's not that important. There's the relationship between the height and the number of nodes is logarithmic or exponential depending on which direction you look. Cool? I think that's pretty cool. Cool. So what would an iterative binary search look like? Well, here's an iterative binary search. Have a look at this. I'm going to give you a minute or so to look at this code and make sure it makes sense, because it's important to understand. For those of you wondering what the hell this is, first of all, don't worry too much. You should still be able to figure out what it's doing without understanding what this is. But I will explain it right now anyways. What this means is when we are comparing the haystack at midpoint to the needle, how do I actually want to compare these things? I'm going to compare them with the T classes compare to method. This would only work if T is like sortable, if it has an order defined for it. Yeah?
So why is it different on the first condition?
Because I'm not actually using objects.compare. I'm using this one. I don't know why I'm not doing objects.compare. I don't know, but it doesn't matter. Now, you might remember a little bit from the sorted bag. Compare to is that thing that returns a negative number if the one number comes before the other, a positive number if it goes that way, or 0 if they are equal. So let's take a moment and walk through this code. We start with the low index at 0, the high index at the length of the array, and the midpoint is going to be, well, the midpoint. Okay? How do we calculate the midpoint? Well, welcome to grade 9. So then I say, okay, well, the low index is less than the high index. That's going to be our case. Because think about it for a second. Every time I guess, I'm going to guess the midpoint. And if you say that, hold on, low, high, does that make sense for you? Or am I doing it? Low? Should this be low for you? Low? Yes, low, high, okay? I always guess the midpoint. So if I guess the midpoint and you say higher, the low index, or the low, will become the mid, okay? It'll actually become the mid plus 1 because I guessed the middle, right? So as we go, the low and high are approaching each other, But there will be a point, if we don't find the thing we're looking for, there will be a point where they cross each other. And when that happens, it's not there. So that's what that while is. While low is less than high, do this. Otherwise, return not found. So if haystack at midpoint compared to needle is 0, we found it. Return midpoint. Great. Otherwise, we say, okay, well, what number, needle, how big, or midpoint, how does it compare to needle? If the high index would become midpoint minus 1. Right, so if the needle comes before the midpoint, the high index should become the midpoint minus 1. So think of it. Let's say it's 100, and I guess 50. And you say, no, it's less than the number at index 50. That means I want to consider all the numbers between 0 and 49 now. All indices between 0 and 49. I don't want to guess 50 again, right? That's what the minus 1 is. Cool? Otherwise, do the opposite. Don't say the high point is now the middle minus 1. Say the low point is the middle plus 1. And just keep doing this until we find it. Effectively, do what I just did right here. Like what, 20 minutes ago? Right? Just keep updating. Pick the middle. Always find the middle. Cool? That's the idea. Don't worry about being an expert and understanding this 100%. It's fine if you're like, yeah, I've got the idea. That's what I care about. Because that's the algorithm. If you understand the algorithm, you can recreate this. But that's the iterative version. Here's the recursive version. And you might look at this and say, like, well, it looks just as complex as the other one. But I disagree. I think this one's a lot nicer. Recursive binary search, needle haystack, and if we scroll over, I'm guessing it's going to have high index, low index, and midpoint as parameters. Low index, high index. Oh, I guess no midpoint. We can calculate that. So the recursive binary search takes the needle, haystack, and a low and a high. First time we call this, the low should be 0 and the high should be the last index. If low is greater than or equal to high index, we didn't find it. Okay? Return not found. Otherwise, find the midpoint. That's how we find the midpoint. If haystack at midpoint is the thing I'm looking for, return the midpoint. Otherwise, do the comparison, but just call the function again. Do the whole function again, but with the high index being the midpoint minus 1, or with the low index being midpoint plus 1, depending on which side of the collection we need to continue searching. And to me, look, it's the same algorithm. It's the exact same algorithm. One's iterative, one's recursive. But the algorithm is the same. And to me, this is more natural, in a way to like explain what the algorithm is. Oh, just do it again, but update what the low end is or the high end, right? Literally do it again by calling the function again. Yeah.
So for the comparison, if it's greater or less than 0, which side is that?
I always get it mixed up, but I'm pretty sure it's when doing objects.compare, if midpoint is bigger than needle, so if the number is plus 1, I think that means midpoint comes after needle, which,
Saying if you were to compare like two integers,
well, hold on, let me,
minus the second one and then decode that.
well, that's if we're doing like dot compare to, like the first one with haystack midpoint. If that was a negative number, midpoint comes before it. If it's a positive number, that means it comes after it. I think the order is probably the same here. Midpoint, so if it's greater than 1, that means it must be, no, I must have it backwards then. I always mix it up. Every time I do it, I relook it up. So, I don't know. Don't worry too much about it, because I always look it up again. And for what I mean is you go back to the Java docs and go like compare to, you look it up, and then it says the order that it matters.
Yeah, I think it is that because you're comparing the against the needle instead of the needle against what's in the list.
Right, that makes sense. If the number at the middle is bigger, that means the needle must be over here, smaller. Meaning the high index should now be the middle minus 1. So I was right, but I still always get it mixed up. And see how sure I am of it? I'm so sure that I would still check it again anyways. Cool. Any questions about these ideas? The takeaway of this topic is I showed you a linear search and a binary search. And we analyzed it, right? One's linear, one's logarithmic in terms of computational complexity, so one's better than the other, but it requires that the data is sorted, ordered in some way. But the big key takeaways I want to emphasize is I showed you an iterative and recursive version of the linear search, but the algorithms were the same, despite one being iterative and one's recursive. And the same thing with binary search. That's what I really want to hit, okay? So yeah, any last questions before we move on? Yes?
If you're calculating the midpoint and you get a 0.5, what would that do?
Well, assuming this is an integer, it would always round down. Round down, it truncates. Yeah. Good question though, but yeah, always go to the lower index.
You're writing in Python, you just slash that.
Yes. Otherwise, integers and indices and floats and Python 3 bad. Yeah. Yeah. Because it doesn't make sense, right? When you do, if I'm dividing two integers and I do division, I better get an integer back. I can't get a float. But in Python, it's like, oh, here you go. This is what you wanted, right? I don't know why, I don't know what they were thinking. That was a huge mistake. Let me clarify.
So it's not strongly typed. So then,
But it is. Everything still has a type.
yeah, but it's not strongly typed when you're writing the code though.
But no, it is, though. It's just, it's not like static. So the problem is, in all of these programming languages that have been big, if you divide the integer 5 by the integer 2, what do you get? 2. And you're going to say, no, it's 2.5. No, it's not. How many times can I get 2 out of 5? Twice. Remainder 1, who cares? I needed to get an integer back. If you give an operator 2 integers, you better get an integer back. And that's the way it's worked. It makes sense that it works that way, and that's the way it's worked for decades in all these different languages. And it worked that way in Python as well. Until Python 3 came around, and they're like, you know what? Screw all of you. I'm going to break all of your old code just for fun. There you go. And they changed it such that when you do division, it'll automatically give you the float if it has a decimal, which is so weird to me. It doesn't make any sense. They give you the integer division operator, which is //, but to me, they did it in the backwards order, where everyone expects it to do integer division when you do regular division on integers, so just do that, but make the special one okay, do floating point division. Well, whatever. It is what it is. So imagine having all your code in Python 2 that depended on integer division, and then Python 3 comes out and it's just like, yeah, you're screwed. That would suck, right? Yeah, it would. Okay. I'm sure there is someone that can tell me exactly why, and there's a nuanced reason why they did it. It's still stupid, though. Okay, any last questions? All right, trees. We've talked about them informally, but they're nonlinear data structures. The data doesn't have a natural, obvious, linear, sequential ordering. And what I mean by that is, like, look at this. And if I say, here, you're at the root directory of C drive. And I say, what comes next? What do you say?
All three of its children.
You're like, what's the one thing that comes next? Documents and settings. Why? Because I don't know, it was to the left, and that makes sense. But did the order of the elements that way even matter? I don't, like, it was, right? It's not as obvious for when I say like, okay, you're sitting right there. Who's sitting next to you in that row? The one only possible option, right? And who's sitting next to you? Well, yeah, exactly. You got two. But if we're going in one direction, there's always one option. Here you're like, well, I don't know. Right? So it's nonlinear. And these things pop up everywhere. Anything that's like hierarchical. Hell, you go look at like a table of contents of a book. That is a tree structure. In fact, maybe I can kind of show you here real quick, right? Like if we click here, see, like this is a small one, but the root of this tree would be tree ADT. And then there's only one subsection, so there's only one thing below it. That would say definitions and terminology, and under that there's several other ones. And yeah.
If you were to make like three things that one key access, would it return all of them in
That-
a dictionary? Or a hash map? Like if you were to set a key for three different things?
You could make it a list, otherwise it's going to just be the most recent thing you set it to.
I'm not, yeah, okay, yeah. And I'm not sure where that fits into this. Keep that in mind, and maybe we'll pick that up on Tuesday or whatever, right? But yeah, trees, they're everywhere. And why is it called a tree? Well, because, it goes like this, but upside down, because that's what we do. Now, there's a bunch of definitions, and the rest of this topic is just definitions. And you know what I hate? Definitions of things. I hate it because to me it becomes trivia. But I'm going to tell you a secret. Every other computer scientist feels the same way, and they hate definitions of things. So thank God all of the definitions are so obviously intuitive that it's not going to be a problem. The thing at the bottom of the tree, which is always the top, is called the root, for example. The things at the end, what do you think you call those? Leaves, right? So, anyways, I'm not going to start throwing the definitions at you right now. We don't have time to go through them all. But on Tuesday, we'll start talking about the definitions. But don't worry too much. The definitions are fairly obvious that you should be able to follow along. And the ones that aren't obvious, no one uses because they're too obscure. All right, I'll see you later.